Imagine you are sitting in the hot seat.
Oh, yeah, the dreaded hot seat.
Right. It is the final round of that, like, high-pressure AI engineering coding interview you have been preparing for all month.
The one that makes or breaks the job offer?
Exactly. The interviewer looks at you across the desk, slides over a laptop, and just drops the anchor problem right in your lap.
Let me guess. It sounds deceptively simple.
Oh, totally. The prompt is just find the top 2 highest paid employees in each department.
Ah, the classic top-end problem.
Yeah, so let's rapidly lay out the data set you are staring at on the screen. You have an employees table.
Right.
Okay.
What are the numbers?
So in the IT department, you are looking at Amit making 50K, Neha making 70K, and John also making 70K.
Got it. So there is a tie in IT.
Yep. And then over in the HR department, you have Raj making 60K, Sarah making 65K, and Priya making 60K.
Okay. Pretty standard setup.
So I want you to literally pause and think right now. Like, pause the playback if you need to, and think about how you will solve this interview coding question.
I bet I know what almost everyone is thinking of right now.
Well, hold that thought for just 1 second. Welcome to the AI and ML YouTube channel by 60 Seconds Academy. Here we focus on practical and application-based understanding and concept clarification so that you can be industry-ready and apply your knowledge to real industry projects.
Which is exactly why we are tackling this specific interview trap today.
Right. So today, our mission for this deep dive is to give you an intuitive, rock-solid understanding of SQL window functions.
Because by the end of this deep dive, you will confidently solve these top-end problems. You'll be able to handle ties deterministically and think entirely in terms of AI feature engineering.
All while completely bypassing the catastrophic trap of the Group P by WAS.
Yeah, addressing that trap is honestly the perfect place to start.
Because I'll admit, my brain went straight to Group P by Y when I first saw this.
See, that is the reflex for most candidates. They hear a problem structured around departments or categories, and they just immediately start writing an aggregation.
Yeah, you hear each department, and your hands just type out Group B by Y dept. It is like the fundamental tool we are taught for summarizing categorical data.
But if you paused a moment ago and mentally drafted a query using Group E by Y, well, you walked right into a fatal error for this specific architectural requirement.
Wait, really? A fatal error. But the logic seems sound. You group by the department, you select the max salary, and you move on.
It seems sound until you look really closely at the exact constraints of the prompt. The constraint is the word employees.
Oh, right.
Yeah, the interviewer did not ask for the highest salaries per department. They asked for the top 2 highest paid individuals.
Ah, I see. So why does Group PY crash and burn here exactly?
But to understand that, we have to look at what the SQL engine mechanically does to your data structures in memory. Like, Group E by Y collapses rows.
It collapses them.
Yes, it evaluates all the records belonging to the IT department, does your requested aggregation, and then forces the output into a single, unified row for that entire group.
So the individual row-level detail is just, what, completely eradicated?
Exactly. Amit, Neha, and John cease to exist as distinct entities in the output matrix. They get blended into one single representation of the IT department.
Wow, okay. It actually reminds me of throwing ingredients into a blender.
Oh, I like that analogy.
Yeah, like you drop in strawberries, bananas, and spinach, hit the button, and you get one aggregate liquid. You get a fruit smoothie.
Right, a very healthy aggregate.
Exactly. But for this problem, the interviewer is asking you to reach into the resulting mixture and pull out the 2 largest intact strawberries.
Which is physically impossible. You
Yeah.
cannot extract specific data points from a data set you have already fundamentally collapsed.
Once the data is pureed, the original structure is just gone forever.
Completely gone. So the alternative to this aggregation blender is the core mental model for window functions.
Okay, so what is the mental model the listener needs to adopt?
The mantra you have to internalize for any advanced coding round is this compute without collapsing.
Compute without collapsing. I like that. So we need to run aggregate math, like identifying max values or ranks, but without destroying the underlying row architecture.
Exactly. Let's visualize the database engine working under the hood to achieve this. When you invoke a window function, the engine does not blend the data.
Okay, so what does it do instead?
Imagine it temporarily splitting your table into isolated memory partitions, like little mini tables based on the categories you define.
Oh, so it dynamically creates one temporary partition just for IT, holding Amit, Neha, and John.
Right, and it spins up a parallel partition for HR, holding Raj, Sarah, and Priya. The logic then executes inside each of those isolated environments to rank the salaries.
So the crucial mechanism is what happens next, right? Because it doesn't return a summary.
No, it doesn't. Once the engine finishes that localized ranking, it maps those newly calculated ranking values directly back onto the original distinct rows.
That is wild. So everyone retains their primary key identity. Amit is still Amit, making 50K.
Yes, but the output now features a brand new computed column appended to his record. And that column indicates his rank within the IT partition.
Okay, so just to summarize that, group P by Y forces an n-to-1 transformation, returning one row per group.
Exactly.
But a window function executes an end-to-end transformation. You maintain every single original row, but you augment them with relational analytics.
You nailed it. So moving from the conceptual engine to the physical code, we have to write the syntax to actually construct these partitions.
Right, the syntax, the foundation always involves defining the function, right? Like followed by the over clause.
Yep, the over clause is the secret sauce.
Yeah.
Inside that over clause, we dictate the behavior using partition by and order by.
Okay, break those down for me.
Sure, the partition by command instructs the parser on how to slice the data into those mini tables we talked about.
So writing partition by depth gives us the IT and HR splits.
Exactly. And then the order by command defines the logical sequence inside that isolated partition. So to surface the highest earners, we use order by salary DSC.
Wait, I see a massive vulnerability in our sample dataset if we just run a basic row number function over that partition.
Oh, what are you seeing?
Look at the IT department. Amit is clearly row 3 with 50K, but Neha and John both make exactly 70K. They are tied.
Ah, the tie trap. Yes.
If we ask the engine to assign row number 1 and row number 2, the logic is inherently ambiguous, isn't it? Who gets rank 1?
And ambiguity in data engineering pipelines is totally unacceptable. A senior interviewer will immediately drill into this exact edge case.
So what happens? Does it just guess?
Well, row number is what we classify as non-deterministic when encountering identical values. The query optimizer doesn't pause to ask for clarification.
Right, it just executes.
Yeah, it simply reads the data pages from the disk. Whichever record it encounters first in the memory block, Neha or John gets assigned row 1, the other gets row 2.
Wow. So if the disk storage shifts, or like if the index gets rebuilt, the order could just flip the next time the pipeline runs.
Exactly. And building a machine learning pipeline on non-deterministic data means your training features will shift randomly between epochs.
Which means the results become fundamentally irreproducible. That's a nightmare.
A total nightmare. So securing deterministic outputs requires explicit tie-breaking logic. You never leave sorting up to the physical memory layout.
So how do you fix it? The pro fix.
You append a secondary criteria to the clause. Something like order by salary DESC, EMPID ASC.
Oh, I see. So you are forcing the engine to evaluate the tie. Sort by salary first, and if 2 records return the identical integer, evaluate their unique employee ID.
Right. Whoever was hired first, meaning the lower ID, takes the higher sequential rank. The ambiguity is completely eliminated.
That makes so much sense. But deterministic sequencing isn't the only way to handle a tie, right?
No, it's not. Sometimes business logic dictates that if Neha and John generate the exact same value, they must share the exact same rank.
Like they're both genuinely in first place.
Exactly. And this requirement shifts us away from row number and forces us to utilize rank or denser rank.
Okay, so what is the actual difference between rank and denser rank?
It centers entirely on how the sequence behaves immediately after the tie is resolved. Let's trace the math.
Okay, let's do it.
So if Neha and John both lock in at rank 1, a standard rank function will recognize that 2 positions have been consumed.
Oh, so it skips the number 2 entirely.
Yes. When it evaluates the next record, which is Amit, it assigns him rank 3. The output sequence is 1, 1, 3. The gap is mathematically preserved.
I get it. And denser rank alters that continuous numbering logic, right?
Precisely. It ensures the ranking values remain dense, completely ignoring how many entities occupy the previous tier.
So Neha and John receive rank 1, and then the engine moves to the next distinct salary value and simply increments the rank to 2.
Yep. Amit receives rank 2. The sequence is 1, 1, 2. No gaps.
Okay, so summarizing the foundational triad here, row number yields strict sequential integers with no duplicates, but it requires aggressive tiebreakers.
Correct.
Rank allows duplicates but generates gaps in the integer sequence. And denser rank allows duplicates and strictly prohibits gaps.
That is a perfect summary. But, with the data successfully ranked and augmented, the core problem still remains.
Right. The prompt requires us to actually find the top 2. And right now, we just have a newly computed column containing the ranks.
Exactly. And the instinct for most beginners is to just filter the output right then and there.
Yeah, I would organically write my select statement, construct the denser rank logic, alias it as rank-goal, and then simply slap a where rank-goal HL2 at the bottom of the script.
It reads perfectly logically from top to bottom, doesn't it?
It really does. Why wouldn't that work?
If you submit that syntax, the database will throw an immediate execution error. The query fails before it even runs
Wait, why?
because it violates the SQL order of operations. The parser doesn't evaluate the query from top to bottom like a standard Python script.
Oh, right. The physical execution pipeline evaluates the clauses in a strict sequence.
Exactly. When you submit a query, the engine first locates the data via the from clause. Then, it immediately applies the row-level filters in the where clause.
I see. And only after the data set is filtered does it move to the select phase, which is where it projects the columns and executes window functions.
You've got it. So you are attempting to filter rows based on a mathematical computation that hasn't happened yet.
Wow, it is literally a fundamental timeline paradox. The engine reads where rank call to 2 and has no memory allocation for rank call because the select clause is still pending in the execution queue.
A timeline paradox is a great way to put it. So, resolving that paradox requires structuring the query in two discrete phases.
Is this where we bring in a CTE, a common table expression?
Yes, the CTE upgrade, or the industry standard solution. We have to force the database to materialize the computed ranks before we attempt to filter them.
Okay, so we encapsulate the entire window function query inside a with statement, like with rank employees AS, and then our query inside parentheses.
Exactly. The engine runs everything inside those parentheses first. It partitions the data, resolves the dense ranks, and writes the resulting matrix into a temporary holding state in memory.
And by establishing that temporary state, the initial query is completely resolved.
Right. And the second phase is writing an outer query that selects from that CTE. Just a simple select from rank employees where rank yields 2.
Because rankle was fully computed and materialized in phase 1, the where clause in phase 2 can read it and filter the dataset without throwing an execution error.
It's clean, readable, and exactly what senior engineers look for. The architecture shifts from a single procedural block to a modular pipeline.
So when the interviewer drops this anchor problem, the most powerful thing a candidate can do is narrate this architecture aloud while typing, right?
Oh, absolutely. The think aloud script is crucial.
Okay, so you should say something like, we need ranking within groups without collapsing rows, so I'm using window functions. I'm using denser rank instead of rank because I don't want gaps when ties occur.
Perfect. And then you add, because window functions evaluate in the projection phase, I am wrapping the logic in a CTE to materialize the ranks, allowing the outer query's where clause to filter for the top 2 records.
That sounds incredibly professional. Narrating the engine mechanics proves you aren't just memorizing syntax, you know? It shows you understand how the parser physically interacts with memory.
And that's exactly what they want to see. But interviewers will often attempt to push past this by altering the requirements slightly.
Oh, what do?
They won't ask for the top 2. They will pivot and ask you to find the nth highest. For instance, find the second highest salary in the IT department.
Okay, the standard analytical hack for finding a specific offset is using limit and offset, right?
Right, that's what a lot of people try.
Like, a candidate might query the IT department, sort the salaries in descending order, use offset 1 to skip the absolute highest value, and then use limit 1 to isolate the next record in the queue.
And that approach is a massive red flag.
Really? Why?
Because offset skips a physical row in the output matrix. It does not skip a mathematical value. Let's apply that to our IT department where Neha and John both make 70K.
Oh man, I see it already. The engine sorts them. Neha is row 1 with 70K, John is row 2 with 70K, Amit is row 3 with 50K.
Yep. So what happens next?
Offset 1 skips Neha entirely. Limit 1 grabs John. The query outputs 70K and claims it is the second highest salary.
Which is mathematically false. 70K is the highest salary. The true second highest salary is Amit at 50K.
Wow. So the limit and offset architecture fundamentally breaks down the moment the data contains identical values.
It completely shatters.
Yeah.
The only robust solution is routing straight back to the CTE structure we just built.
Right. So instead of filtering a range with less than or equal to 2, we execute an exact match filter, like where rankles to 2.
Exactly. Because denser rank evaluated Neha and John as a shared rank of 1, the engine safely assigned rank 2 to Amit.
So the where clause mathematically guarantees the retrieval of the true second highest value. It's completely immune to the volume of duplicates at the top tier.
Exactly. Mastering this logic is a strict requirement for database administrators, obviously,
Yeah.
but we have to contextualize why an AI and ML engineering candidate is being grilled on this specific SQL architecture.
Yeah, why does this matter for ML roles? We aren't just pulling reports.
No, we are building the data infrastructure that feeds predictive models. Window functions are the absolute backbone of feature engineering.
That makes a lot of sense because machine learning models do not learn from isolated data points, right? They learn from relationships and context.
Right. A single transaction record is virtually useless to a neural network without the context of the user's historical behavior.
Can you give an example of how that works in practice?
Sure. Consider building the feature set for a real-time recommendation algorithm on a streaming platform.
Okay.
The model needs to understand sequence and behavioral momentum. To build a session ordering feature, you write a SQL pipeline that partitions the telemetry data by userid, orders it by the event timestamp, and computes the row number to map out the exact sequence of clicks.
Oh, wow. Or take a fraud detection model evaluating financial transactions. The model needs to analyze velocity, right?
Exactly.
You need a feature that calculates the rolling average of a user's transaction amounts over the last 5 purchases.
Yep, and how would you build that?
You write a window function partitioned by accounted, ordered by time, and bounded by a trailing window of 5 rows. The engine computes that rolling average without collapsing the individual transaction records.
Spot on. You are physically constructing the multidimensional tensors that will eventually become the training set.
And if your feature engineering pipeline uses a non-deterministic sort or miscalculates a dense rank, you introduce garbage data into the training loop.
Exactly. The model learns flawed relationships. And whether you are writing raw SQL for Snowflake or translating this logic into pandas or PySpark using like the groupie transform methods, the mathematical constraints are identical.
So the real test in the interview is pattern recognition. An AI engineer doesn't just memorize the syntax, they recognize the triggers hidden in the prompt.
Yes, triggers are everything. When the interviewer uses phrases like top per group, nth highest, rolling context, or rank within category,
The candidate immediately recognizes that the problem requires relational computation without row collapse.
recognizing those triggers allows you to reach for the correct tool without hesitation. Let's construct a mental map of the entire SQL logical ecosystem to finalize this framework for the listener.
Let's do it.
The language provides specific tools for specific data transformations. When you need to strip away irrelevant raw data before doing any processing, you utilize where.
Right. And when you need to compress thousands of rows into overarching summary metrics, you utilize group by Y.
Exactly. When you need to evaluate and filter those newly compressed summary metrics, you utilize having.
Okay. And when you need to widen your data set by bridging disparate tables together, you execute a join.
And finally, when you are required to analyze data contextually within localized groups, but you absolutely must preserve the individual, granular, row-level architecture.
You deploy a window function. The logical tool belt is entirely complete.
The mechanics really should be second nature. So let's enforce that with one final review for the listener.
I love a good pop quiz.
Think back to the beginning of the problem. If an interviewer asks you to compute the ranks of individual employees within their respective departments, why does Group E by Y fundamentally fail?
I want you all to answer this out loud. It fails because it removes row-level detail. It aggregates the entities into a single categorical output, destroying the individual records required to complete the prompt.
Exactly. The logical architecture is sound, but, logic is only half of the engineering equation.
What's the other half?
Before you tackle your next system design round, consider the physical reality of the hardware. We know how the query parser evaluates a window function, but what happens to the underlying memory infrastructure when you scale this up?
Oh, man. Like, imagine executing a partition by userid order by timestamp over a data set containing 4 billion rows of user telemetry to build a predictive model.
Right. A CTE forces the engine to materialize that result set in memory. What happens when the size of those partitions vastly exceeds the available RAM on your compute cluster?
That is a scary thought. How does the database engine handle the spill-to-disk mechanisms? And how do distributed computing frameworks physically shuffle that data across network nodes to calculate a global rank without just crashing?
Pushing beyond the syntax and evaluating the physical constraints of distributed memory allocation is exactly what separates mid-level coders from staff-level AI engineers.
Well, we will dissect memory optimization and distributed query tuning in a future deep dive. That bridges the gap between writing code and designing enterprise systems.
Definitely. It's the next logical step.
So, for your immediate progression in the 60 Seconds Academy curriculum, prepare for DSA Lecture 6 two-pointers, where we will translate some of these sequential processing concepts into core algorithmic patterns.
That's going to be a great one.
Until then, when you find yourself in the hot seat and the interviewer demands the top two of anything, remember the mechanics. Do not collapse your data.
Keep your rows pristine.
Partition your windows carefully and engineer your features with absolute precision.